welcome to Honors Physics Podcast. This is proof of equation 7.8a, which works for an elastic collision where our object 2 is not moving to start. So in an elastic collision, we have the conservation of momentum, and we also have conservation of kinetic energy. So if we have an object that collides with a stationary object, afterwards, we're looking to see what the relationship is between the velocities. So we know that our initial momentum is equal to m1 times v1. I leave off the m2 v2 term because this second object is not moving. Our final momentum will be equal to m1 times v1 final plus m2 times v2 final. Now because this is a collision, momentum is conserved, so we end up with the equation m1 v1 equals m1 v1 final plus m2 v2 final. And just a quick explanation of these variables: m1 is the mass of object 1, v1 is the initial velocity of object 1, v1 final is the final velocity, and v2 final is the final velocity of object number 2. And the concern is in this problem that we would not necessarily know our v1 final or our v2 final, so we have to bring in our kinetic energy equations. We say that 1/2 m1 times v1 squared, which is our initial kinetic energy of the system, is 1/2 m1 times v1 final squared plus 1/2 m2 times v2 final squared. I'll call the momentum equation equation number 1 and the kinetic energy equation equation number 2. If we solve in equation number 1 for v2 final, we end up getting v2 final is equal to 1 over m2 times the quantity m1 times v1 minus v1 final. If we take that equation, which I'm calling number 3, and we plug it back into equation number 2 up here, we get the following answer. By canceling out the 1/2s, which are in front of every single term, we get m1 times v1 squared equals m1 times v1 final squared plus m2. Now we have this whole term up here that equation 3 is squared. So we've got our 1 over m2 times m1 times v1 minus v1 final. And this whole term here is squared. In looking at this, there is a 1 over m2 squared inside of parentheses, so we indicate m2 over m2 squared here. We are multiplying by our m1 squared again, so we're multiplying by m1 squared. And then we have this term, which I will keep as is, v1 minus v1 final squared. The rest of that term is going to be m1 times v1 final squared, and that will equal m1 times v1 squared. We have a number of m1s that we can cancel out, this one here, and one of these here. We can cancel out the squared for the m2 and leave this here, so we're left with the following. v1 squared is equal to v1 final squared plus m1 over m2 times v1 minus v1 final squared. If I'm solving for a relationship between v1 and v1 final, I need to solve for one of these and express it in terms of the other. So I will bring my v1 final over to this side first, and it'll become apparent why we do that in just 1 second. We're left with v1 squared minus v1 final squared equals m1 over m2 times v1 minus v1 final quantity squared. I'll distribute the m2, and I'll be left with m2 times v1 squared minus v1 final squared. Now we should start to notice that we have something kind of interesting on the left and the right hand side. We have this squared term, which is essentially v1 minus v1 final times v1 minus v1 final. And on the right hand term, this is a difference of squares. So when we write that out and factor it, we get m1, we get a v1 minus v1 final times v1 plus v1 final. We still have our m2 in the front here. And now we have this term here. Actually, one of those two terms on the right-hand side. So we'll cancel them out. We're left with m2 times v1 plus v1 final equals m1 times v1 minus v1 final. If we solve this for v1 final in terms of v1, we are left with expanding this, m1 v1 minus m1 v1 final, m2 v1 plus m2 v1 final. Bringing this term over here, bringing this term over here, we can factor out a v1 final here to be left with m1 plus m2. And on the right-hand side of the equation, we can factor out a v1, which I'll put at the end here. And we're left with m1 minus m2. So then our result is that v1 final equals m1 minus m2. So the difference of the masses divided by the sum of the masses multiplied by our initial velocity. And we see that this works because in an elastic collision, if two objects are colliding that have the same initial mass, we should get our first object, our moving object, to stop. And if m1 equals m2, then we see that this term up here gives us a 0. So the second object gets all of the velocity, the first object comes to rest. Again, this is equation 7.8a from your textbook, and this is now a valid and useful equation.